Viktor Sokolov from M and S decisions, and also from Marchuka Institute of Numerical Mathematics. And the title of today's presentation is New Methods for Systems Pharmacology Modeling and its Application for Assessing the Effectiveness of Diabetes Treatment. Please, Victor, you can, your slides, okay. Well, so kind of, all right, so you can start your presentation, please.
Thank you very much for the introduction. Maybe just a few additional words on my side. First of all, can you hear me well?
For me, it's fine.
Yes.
Great. Yeah, so a short background about this work. I've graduated from the Moscow State University Department of Bioengineering and Bioinformatics. It was quite a long time ago. It was in 2010. And since then, I was working in scientific consultancies associated with drug development, doing mathematical modeling in drug development, essentially, primarily focusing on mechanistic models. We will talk about them in detail today. And gradually throughout the years, I've been building up the materials to write a PhD thesis. And this work is basically a presentation of my PhD work. I hope that my scientific advisor, supervisor is Gennady Alexeyevich, and Dr. Kirill Peskov is my scientific consultant and my colleague. I hope you will enjoy the seminar. We will talk about a new method for developing systems pharmacology models. Again, all these terms I will decipher throughout the slide deck. And we will be talking about diabetes today, quite a lot. So let me continue with the slides. Oops, sorry. This is the outline of today's presentation. After a brief introduction, name and objectives, we will discuss the methods, how to build QSP models in drug development. Then we will talk about two mathematical models of diabetes and their application, finally their application. But first things first, let's talk about some definitions. I will try to use as little terms as possible, but the essential one is quantitative systems pharmacology modeling, or QSP modeling. I would say it's already an established abbreviation in the community of drug developers and mathematical modelers in drug development. I will call them pharmacometricians. It's a well-established abbreviation, but what does it mean? Basically, it means very simple thing in concept. It's a mechanistic description of dynamical changes in drug concentration and respective biomarkers in organs and tissues. What are the essential features of the systems pharmacology models? First of all, most often they are developed as systems of ordinary differential equations. That's the first point. The second point, one could characterize QSP models as having systemic parameters. What do I mean by systemic parameters? I mean that we have, in the model, we have constants, rate constants, for example, volumes, concentrations, that are specific to the system that we are trying to model. They are not specific to a certain drug, which is typical for PK/PD models, where basically pharmacodynamics is empirically coded as a function with, but suitable and applicable only for the selected compound. So that's the general idea. Why QSP models are important in drug development? Because their area of application is quite wide. We can use mechanistic models for identifying new biological targets, right? Molecules that we want to interact with. We can use mechanistic models to predict the effect of existing drugs in new diseases. These are translation to other diseases. We can use the modeling to predict first-in-human dose. When you have preclinical data in animals and in vitro, you can predict, use mathematical modeling to predict optimal dose, starting dose in human clinical trials. Then effectiveness and safety of combination therapies. Also benchmarking competitors within a single mathematical framework. We will talk about this today. And of course, mechanistic hypothesis generation, maybe not the best phrase, but of course, if we, what's the model? The model is a hypothesis of associations, right? Our understanding of the mechanisms. So, of course, yeah, we can test different hypotheses regarding the mechanisms of actions of certain events. All right, so hopefully this is clear. I suppose, yeah, if you have any questions, please interrupt me at any point. So I suggest, yeah, we can do it like this. But there is also a few very significant challenges in application of such models in drug development. I'm emphasizing drug development because this is a very conservative domain, strictly regulated by what we call them regulatory authorities. It's like Ministry of Healthcare in Russia, FDA in the US, EMA and in Europe, etc. And again, this domain, drug development, is very strictly regulated. And in order to effectively apply QSP models in drug development, we need to overcome several limitations. These limitations were summarized in several papers wrote by FDA colleagues, and they include, first, lack of systematic approach and reproducibility in data collection for the model development. I will elaborate on each on each point throughout the slide deck, and hopefully it will become very transparent. But for now, yeah, that's the first point: how we collect the data, how to be comprehensive and evaluatable in terms of the reproducibility and completeness of the search. Then the second point is the absence of unified criteria for assessing model quality. Again, I will explain it in detail in the subsequent slides. Third point is the limited ability to account for real variability in clinical response. And the last point is the time it takes to develop such models. I think all of the audience here knows and developed much more models, like mechanistic models, than me. So you know how tough it is to create a model, how long it might take. In drug development, you are always working within a strict timelines as well. So you need to have some tools. The point here is that you need to have some tools that you can use to develop the models as quickly, as robustly as possible. So here are these 4 challenges. So how does our work come into play here? Well, the aim of our work is to develop a model, a method for developing these QSP models, systems pharmacology models, implement it into a software and apply in drug development questions. And to meet this goal, we solved the following objectives. First, we created a modeling method. We implemented in software package in R and monolith environment. Then we developed two models using this method, model of kidney glucose reabsorption, and then an integrated model of diabetes. And finally, we applied these models in order to answer several practical questions regarding to the effectiveness of anti-diabetic therapies. Probably, yeah, let's skip this slide. It's basically key results. We will come back to them in the conclusions either way. So let's start with the method. Please bear with a little bit of theory for now. Then we will switch to the examples, to the models, where I will attempt to illustrate how this method is actually applied in action. So let's start to address key challenges stated by the FDA and in this presentation. We propose a methodology for systematic and reproducible literature search. It basically consists of two parts, what we search for and how we do it. We propose that every project, QSP project, should include the systematic search for three directions. That's core biology, existing models, and quantitative data necessary to build the model. The details, what exactly is meant by these points, they are listed here on this slide. But also very important is not that only a modeler should go through these 3 points, sort of this checklist before initiating the modeling. It is also important to document information sources, search strategy, and selection process. By combining these two things, by applying these two things, we can arrange a standardized database of relevant articles and quantitative information that we can effectively utilize in a subsequent modeling. This might seem like maybe partially quite obvious, but again, for the sake of quality control and reproducibility, very little papers, very little modeling works do this comprehensively, do this search comprehensively. And what we propose here is reminiscent of the, well, at this point already mandatory methodology used in systematic reviews and meta-analysis called PRISMA guidelines. If you are interested, yeah, we can, I can provide you with the links, etc. Quite an interesting thing. That's the first part, of our method, how to collect the data. Then, second part of our method, how to select the structural model. Again, I will illustrate on the subsequent examples in diabetes. But overall, I think the most important points are, you can derive 3 most important points here. First, apply the enzyme kinetics theory to create the equations. Second, by default, spatial distribution is important for us because it's, for drug development, it's always the question of how much target versus how much drug you have in the site of action. So typically model variables are assigned to compartments, which are essentially physiological volumes. And the third principle of creating a structural model that we propose to consider in the method, that the models, the QSP models, are usually quite large in their size. Large is a relative term. We will be talking about tens of ODEs and quite a lot of parameters, obviously. We need to reduce the dimensionality when solving the inverse problem, when calibrating the parameters. Obviously, we should fix parameters based on the prior knowledge. We should derive initial conditions from the model parameters, and we should solve the inverse, well, when possible, we should solve the inverse problem sequentially by dividing our full model into submodels. Again, I will demonstrate all of these aspects on subsequent modeling exercises. For now, it's more like a theoretical introduction. Second, the next third part of our modeling method, we need to establish unified criteria for assessing model quality. Here we divide these criteria into 6 parts. The first one is the numerical criteria based on maximum likelihood methods. So we propose to use a Kaiki criterion as a model selection criterion. Then we should consider practical identifiability of model parameters. Typically, we do this by calculating a variance-covariance matrix from Fisher information matrix and calculating standard errors of parameters, and if relative standard errors of parameters, so in percent, exceed 50%, we cannot consider this parameter to be identifiable, and the model structure should be reconsidered. Alternatively, we can use likelihood profiling or bootstrap, parametric, non-parametric, but usually it's a little bit computation heavy for such models, so might not be optimal. Then we should consider lack of correlations between model parameters. We should, of course, evaluate goodness of fit plots. There are a lot of goodness of fit plots that we consider in our method, including observed versus predicted values, weighted residuals versus time versus predicted values. There are distribution of individual parameters if we have mixed ethics modeling, visual predictive check, etc. Then we should verify the uniqueness of the solution. I mean, the results of the parameter estimation procedure. Usually, this is done by estimating parameters from several times from different initial conditions, from different initial values. And last but not least, very important for QSP models, model validation using independent data. So, if a model meets these 6 criteria, if a QSP model meets these 6 criteria, we propose to consider model fit for addressing regulatory questions in drug development. And finally, we need to account for, we need to understand the interpretation of model simulations or solving the direct problem in the engineering terms. In our work, in my work, we propose several different simulation scenarios. Here we highlight 4 main scenarios. We can perform simulations only with typical parameter values like fixed constants. Then when we should do it, when we are attempting to analyze the system, perform sensitivity analysis. And what it represents, what such simulation represents, it represents a typical trend, a typical subject of a population or a trend of within a certain cohort, things like this. In the second type of scenario, we can introduce uncertainty by sampling parameter values from the variance-covariance matrix that we uncertainty distribution. Then we can generate confidence intervals around our predictions, and when we should use these predictions, for example, when we are trying to benchmark competitors or compare, for example, placebo response with an active treatment, or essentially two different treatment types or two different doses. Third type of simulation, main simulation scenario, is the simulation with that takes into account between subject variability, and this allows to account for the heterogeneity in the response within the population. And finally, we can include both uncertainty and variability by combining the second and third option, which essentially brings us to the virtual clinical trials. So again, this is an attempt to propose a method for accounting for real variability in clinical response. But that's a theory. Maybe some of it might be too obvious, maybe some of it can be unclear. So I would propose to check the examples now to be more illustrative and more comprehensive. The examples will be in the therapeutic area of diabetes. Just a few words about the diabetes. I'm sure everyone heard of this disease. It's unfortunately a very common disease, and it's actually a pandemic. It became a pandemic quite long before the COVID, obviously, and we are talking about two types of diabetes. Type 1 diabetes is the minority of cases, and approximately 10%. And it is caused by the lack of insulin secretion. It's an autoimmune disease. Most commonly occurring type of diabetes is type 2 diabetes. It represents approximately 90% of all cases, and it is caused by insulin resistance of the tissues. And to combat the type 2 diabetes, a certain class of drugs was created. This class of drugs is called gliflozins, or SGLT2 inhibitors. They inhibit reabsorption of glucose from kidneys back to blood. So throughout our everyday life, glucose is constantly filtered. It's a small molecule. It's constantly filtered by kidneys into the urine, but it is almost immediately reabsorbed back. In healthy condition, glucose is reabsorbed back completely. So that's why we typically do not observe any quantities of glucose in urine, or very small quantities. And this is achieved thanks to the work of two transporters, SGLT2 and SGLT1. SGLT2 is responsible for 80 to 90% of all glucose reabsorption in normal state, while SGLT1 contributes to the remaining 10-20%. So as you may guess, when we introduce SGLT2 inhibitors into the system, they block SGLT2 transporter, thereby preventing reabsorption of glucose from kidneys back to plasma. Therefore, glucose starts appearing in the urine. There are, at this moment, on the market, there are several gliflozins, different gliflozins. and their variations, but the three main ones, triad of gliflozins that were developed first were these: dapagliflozin, empagliflozin, and canagliflozin. Three compounds, three competitors. They belong to, of course, different pharma companies. And when SGLT2 inhibitors started, they are currently on the market for several years, or quite many years actually, and they are very effective, but there are still several clinically relevant questions to these compounds. First, they are effective, but not as effective as we want them to be. So, as I mentioned, SGLT2 transporter is responsible for reabsorbing back approximately 80 to 90% of glucose from the kidneys. While when we introduce SGLT2 inhibitors, this number decreases only to 30–50%. So why? That's the question. Second question is that canagliflozin, it seems like it was more effective among the three compounds. So the question is why? And the third question is, of course, there's always heterogeneity in clinical response, always variability. Yeah? Clinical response is always variable. So the question is, which patient characteristics might be associated with the effectiveness of treatment? So several clinically relevant questions that we would like to address with our mathematical models. And we developed two models. The first one is a kidney glucose reabsorption model. We developed it, of course, using the methodology that I have mentioned before in the first part of the presentation. And I will illustrate this. But let's go step by step. On this slide, you can see the scheme of the kidney glucose reabsorption model. It consists of four compartments, four volumes: plasma, first two segments of kidney tubules, third segment, they are called V lumen 1 and V lumen 2. We have bladder, and we have glucose that goes through these compartments and is excreted to the urine. MPG, this is mean plasma glucose. Plasma PK, this is pharmacokinetics of the drugs in plasma. They, of course, are also filtered by kidneys. And these two compartments are essentially the sites of action of the compounds. The compounds inhibit SGLT2 and mostly do not inhibit SGLT1, but we will talk about this a little bit later in detail. The total model, it consists of 37 ordinary differential equations. I will show them on the subsequent slides. And it includes 42 parameters. 25 parameters were taken from the literature, and 17 parameters were estimated based on the experimental data. Regarding the numerical methods, we use implicit ODE solver for STIF-ODE systems. Parameter calibration here was performed using cross region method. But let's talk about the model in detail and draw parallels with the method that I've mentioned. These four equations presented here, these are differential equations for glucose dynamics in lumen compartment, first lumen compartment, second lumen compartment, bladder, and urine. And here we have probably quite a simple system, again, probably because it's all relative. We have mostly first order rates of glucose being transported across the tubules of the kidney. Maybe most interesting rate here is the reabsorption rate. It is based on the enzyme kinetics. I think all of us are familiar with Michaelis-Menten kinetics. So this is essentially it. With competitive inhibition, so we know from the literature, from the publications that glyphosins are competitive inhibitors of SGLT2 transporter. Thus, we can derive this equation to describe how glucose is transported back to plasma and how our compounds, glyphosins, how they inhibit this process.
Excuse me, Victor. Since you suggested us to ask questions during the talk, I cannot miss this occasion because the model, well, it might be simple, but in fact, it's not simple for us because there are many equations and many variables. So please, could you please recall this first variable lum1 in the first equation? What is the meaning of this variable? You certainly told us, but probably I missed or I don't remember. So the meaning of this variable.
Absolutely. So the meaning of this variable is the amount of glucose in, or is the concentration? Sorry. So let's go with concentration. It's the amount of glucose in kidney tubules in the first and second segment of convoluted kidney tubules. So it's the concentration of glucose. And this equation, it consists of three rates. One with a positive sign is the filtration of glucose from blood to the urine with the rate of glomerular filtration. And then we have two negative terms. It's the transition from the first lumen compartment to the second lumen compartment. Here it is. That's a symmetrical rate, right? And then we have, again, with a negative sign, a velocity of glucose reabsorption back to plasma.
Right. The first positive term, you say it's absorption from blood plasma. So you don't have variable, I mean, the concentration, glucose concentration in blood plasma, you don't consider as a variable, right? Or what?
Exactly. In this model, we assume we operate with the, I would say, daily dynamics. I mean, like average daily dynamics. We do not describe the detailed profile of the daily glucose. We will do that in the next model, in the integrated model of diabetes, where we will introduce glucose homeostasis in plasma. Here, both GFR and MPG, these are constants.
Right. Thank you. Continue, please.
Thank you. Enzyme kinetics, that's the first principle. The second principle, that the variables are assigned to the volumes, right? They are interpretable. And here are the volumes that we assign the variables to. Let's continue further with our methodology. I also mentioned that we always want to reduce the dimensionality of the inverse problem. So one approach is basically we need to know initial conditions of the system. Since the physiological system is typically homeostatic in nature, we are not starting from zeros in real life, right? So we already have certain concentration of glucose in lumen 1 at baseline, certain concentration of glucose in lumen 2, etc. And this is just an example how we can derive initial conditions of our system through model parameters. Again, probably as since many of the audience are better mathematicians than me, I think that this concept should be, I suppose it should be familiar, right? So we just assume that the equations are equal to 0. We consider this as a steady state is our baseline. and then derive baseline values like this.
Yeah, excuse me again to interrupt you. Yes, we understand that you, as initial condition, as far as I understand, you take the stationary solution of this
Yes.
of the system. But if it is a stationary solution, then what will change? I mean, this time. If you understand my question, you take a stationary solution, so it does not change with time. So what changes in the model? Where the time dependence comes from?
This is only an initial value. So what I'm trying to say is that we need to start. So we can either calibrate initial parameters, initial values of the system, or we can derive them from the parameters. Thus, we avoid introducing additional parameters into the calibration procedure, because we need to calibrate, we need to have baseline levels of glucose in lumen 1, glucose in lumen 2, glucose in bladder. We know that.
Excuse me. Maybe my question was not very clear. So you have a ordinary differential system of equations.
Yes.
Is it autonomous or not? So the coefficients are not time dependent, right?
Coefficients, yeah, coefficients are not time dependent.
Are not time dependent. So you take a stationary solution of this system.
What changes? Thank you very much. Drug
yes.
changes.
Okay.
Yes.
Okay. Initial condition does not take into account drug, right?
Thank you. Yeah. Let's switch to this slide. Now I understand. Sorry. These are equations for drug PK. Let me briefly explain what happens. So we have several transit compartments to describe the delay in absorption process. Then we have pharmacokinetics in plasma and pharmacokinetics in kidneys. This is what we call minimalistic PBPK model. And we, at the certain time points that we want to model, that corresponds to experimental data, for example, we give a dose to the dosing compartment. In this case, it's drug D, which then starts to travel through transit compartments, then is absorbed to plasma, to the central compartment, distributed to the peripheral compartment, and to kidney lumens, where it actually acts.
So, yeah, I think, excuse me again, I think that I understand now what you say is that first we consider the model without drug. We take the stationary solution of this model as an initial condition, and then we introduce in the model this drug, and it acts on all the system, and of course all this concentration change. Okay, I think I understand. Thank you for your answer. Continue, and sorry for the interruption.
No. Thank you for your questions. It's always a pleasure to discuss. Yeah, and this is exactly as Vitaly Isaacovich just said. And what else? Yeah, about another principle that we calibrate the elements of the system sequentially, because strictly speaking, we have 3 drugs in our system: dapagliflozin, empagliflozin, and canagliflozin. They do not influence each other. I mean, their pharmacokinetics. We do not simulate combined. We don't have data on combination treatment, etc. So it's very simple. What I'm trying to say is that they can be considered separately. We can calibrate PK parameters for one compound separately, so we will have to calibrate only around 5 parameters simultaneously. Then for second compound, then for the third compound. That's also an illustration of the principle of sequential modeling that I mentioned previously. So that's the model, the kidney glucose reabsorption model. First, I will explain the model structure, then how they are applied, validated, their goodness of fit, etc. So, if you don't mind, I will then now describe the second model, an integrative type 2 diabetes model, we just call it integrated because it integrates aside from the PK module and kidney module. They are marked with blue and green colors respectively. We replace this MPG term with a mechanistic description of plasma glucose and insulin dynamics. This is a huge addition because it allows us to describe daily changes of plasma glucose and insulin and their crosstalk. The fourth module, the fourth edition, is a submodel of hemoglobin glycation. Hemoglobin, again, probably everyone heard about this molecule. It can bind with glucose. This is a very slow process, non-enzymatic, essentially. And glycated hemoglobin, which is designated as HbA1c, it reflects the long-term changes in glucose. So it basically represents how high or low your glucose was on average throughout the last 2 to 3 months. And it's a very important marker of diabetes. It is used as a surrogate clinical endpoint, but that's another topic for discussion. And hemoglobin is present in the red blood cells, and this glycation happens in red blood cells. So this model, it has 44 ODs because we only consider dapagliflozin here. It has 49 parameters and 20 random effects. So this is a mixed effects model. It was built on subject level data. The previous model, I forgot to mention, it was built on aggregated data. I will illustrate this later. 33 parameters taken from the literature, 16 parameters estimated. Again, the same solver for ODEs, but for parameter calibration, we use SAEM method, which is stochastic approximation expectation maximization, implemented in Monolix software. It's quite a sophisticated method for handling nonlinear mixed effects tasks. For the sake of time, I was not planning to discuss in detail equations for the full model, but they are available in the slide deck. They are built in the same principle as mentioned in the methods. A lot of equations were first-order equations, physiological compartments, etc. And for hemoglobin, we have several transit compartments with describing the process of glycation, and almost all initial conditions, they are also derived from the parameters of the systems, or in several cases for insulin and glucose, they are calibrated. That was I was talking about. So sometimes you need to calibrate the initial value. So again, we can come back to the equations if we want. I propose to go through the key results, and then we can continue our discussion on the model itself. So here, in slide 21, it's an illustration of our goodness of fit principle. Here you can see goodness of fit plots. For example, top 2 rows. These are observed versus predicted values, diagnostics. Here on the 3rd row, we can see weighted residuals versus individual predictions, or versus dapagliflozin, versus time. So these are different types of model diagnostics. They illustrate that the lowest line, it illustrates that the overall, there is no clear, at least visually noticeable bias in the description of experimental data. Plus, we can, again, we can utilize different types of diagnostics. This is only illustration. We have a lot of it in the thesis, of course. Here's the profiles of time profiles of dapagliflozin PK in plasma on different days, day 1, day 14, different doses, and here we have dots are individual data, empty points observed mean, and line with shaded area, it's model predicted mean with confidence, with prediction distribution. Yeah, it's simulation with variability included, so we sample from random effect distribution and reproduce the observed variability between subject variability.
Victor,
yes.
sorry again.
Yeah, sure.
So just to better understand all these graphs, because many of them, to make sure that we understand them. For example, if you take the right part of this slide at the top, yes, this with your cursor. So here we have one drug administration, right? For example, 5 milligrams or 25 milligrams, right? And then with this one drug administration, you measure, in this particular case, drug concentration in plasma. This
yes.
is what this graph's about, right? And the graphs below, it's after this one administration, you measure the concentration of glucose in plasma, right?
It's even a little bit more complex because this is all clinical trial data from the real clinical trial. So we have day one, but the administration is actually, the drug is given once per day for 28 days. So we have treatment day 1, treatment day 14, and here as well we have pre-treatment data and after treatment at day 2 and day 13, for example.
So in your model, to compare with the data, you have not just one drug administration, but daily drug administration, and all this pharmacokinetics. For example, you have probably exponential decay in drug administration, in drug concentrations, and new administration, and so on. This is how you model it, right? Okay.
Exactly.
And in the left part of this slide with these blue graphs, it's the dependence on what? On drug concentration, or what is it on the horizontal axis?
On the horizontal axis. It depends on the plot. They represent different things. So for the upper row, we have population predictions. It's a typical value. So with one single parameter value, what we call typical parameter value. Actually, it's not really, I should probably remove it because it's less important compared to the next one, which is individual predictions. So basically, we have individual predictions of plasma glucose, plasma insulin, plasma dapagliflozin, and urinary glucose. We can compare these predictions with the observed data that we use for model calibration, and they should match.
Yeah, sorry, but when you say individual prediction, what means individual prediction?
Because we, in this model, in the integrated model, we had individual data for model calibration. What I mean by individual data, it's also called subject level data. I essentially had measurements, time profiles, right? Measurements over time from individual subjects of clinical trials. So I had, like, for example, 300 different profiles, or there was around 50 subjects, if I remember correctly. So 50 subjects. For each subject, I have different profiles, different measurements from plasma and from glucose. This allows me to introduce random effects into the model. Random effects are normally distributed random variables with mean 0 and dispersion with variance, well, usually omega squared, it's estimated. This allows me to compute individual parameter values and their distribution based on the subject level data, if that makes sense.
It certainly makes sense, but I'm not sure that I understand. I'm not sure neither that it's appropriate to discuss now, but just the last attempt. For example, in these graphs at the left, you have this on the horizontal axis, you have numbers from maybe from -6 to 3. Like, what are these numbers? To what they correspond?
-6 to 6. These are weighted residuals. Here we have weighted residuals. This is delta between predicted and observed.
No, sorry. My question is about the horizontal axis.
Sorry.
X-axis. Yes.
These are log transformed values of, for example, urinary glucose measurement. So it's grams, but log transformed. It's a log transformed, amount of glucose in the urine here, concentration of dapagliflozin here, concentration of plasma insulin here, and concentration of plasma glucose here.
Mm-hmm.
It's the measure. Let me try to explain it even better. So we can look here, right, on this plot, for example, this one. We have model prediction, right, and we have data points, individual data points. I can compare model prediction with the individual data points, and I can plot them on the figure like this. So that's what I do. That's it.
All right. Thanks. Continue, please.
Thank you. We have we have more data than I can show here. It's mostly in the backup and in the thesis. But what I also wanted to highlight is an examples of independent validation, validation using independent data. So here's how it looks like. We have the data that we have used for model calibration, right? But we also have a set of data that we do not use for model calibration. Even more, this is a different kind of data. To be exact, this is a data for the experiment called hyperglycemic, stepwise hyperglycemic clamp. It's a certain procedure when a person is infused with glucose so that the plasma glucose concentration is increased step by step, like really like steps in the plasma. We used this data. We predicted these experiments within the model and overlaid our predictions with the observed data without calibrating model parameters, right? We already have them in the system. These are systemic parameters. And we can predict new experiments. And our goal is to check that the model describes the data well, which it does. We can see that the model predictions, these are curves on all plots. Curves match with the data quite well, which is good for us. And again, it shows that the model that we can basically extrapolate with the model, because of course the strength of mechanistic model is the ability to extrapolate beyond the scenarios that are used for model calibration, if that makes sense. At this stage, we can say that the model passed our quality criteria, and it can be used for addressing clinically relevant questions and application in drug development. So several examples of how the model can be applied. First, again, probably a relatively straightforward exercise. We can perform global sensitivity analysis of the response of essential glycemic markers, I mean glucose levels, basically, glucose and HbA1c levels. In response to gliflozin treatment, how this response, how the effectiveness of gliflozin treatment depends on the model parameters. So we select a certain number of parameters that we see most relevant, including the SGLT2 capacity, glucose at steady state, insulin clearance, insulin production, things like these. And then we calculate partial rank correlation coefficient. Again, I won't be going into the methodology. It's relatively standard. Yeah, and then we can assess how glycemic marker, how the change in glycemic markers responds to the changes in certain parameters, and make some conclusions. For example, based on this plot, and the values of PRCC, of course, we can say that gliflozin's efficacy primarily depends on the disease state, meaning the severity of diabetes, as well as the capacity of SGLT2 transporter, maximum capacity of SGLT2 transporter. So what it means in clinic, it basically means that you can choose which patients will respond better to the treatment. But this is kind of obvious. It's important, but yeah, it makes sense. There's nothing too deep here. Maybe next result might be more interesting. If you remember, I mentioned that SGLT2 inhibitor, SGLT2, it is responsible for 80–90% of glucose reabsorption, but the gliflozins, they inhibit reabsorption by 30–50% typically. And here's the experiment, numerical experiment that we can perform. Let's imagine that we will give a dose of dapagliflozin at time point 0. What happens? We inhibit reabsorption through SGLT2 transporter. But since SGLT2 transporter is located before SGLT1 transporter, we basically, by inhibiting SGLT2, we provide more substrate for SGLT1, which starts working at increased capacity and compensates. It basically diminishes the efficacy of gliflozins because of the spatial component, because we increase the amount of substrate down the line, and SGLT1 starts working harder. Thereby, the glucose reabsorption, inhibition of glucose reabsorption is indeed limited by 30–50% in the system. That's another example of model application. Third example is the benchmarking of different gliflozins. I mentioned also before that canagliflozin, it seems to have better efficacy in the clinical trials. First, we can fairly benchmark 3 compounds within a single mathematical framework, because what we all need to understand that competitors never test their drugs in a single clinical trial. So you can observe potentially an increased effectiveness in a competitor clinical trial, but that might be associated with a population that competitor chose. And indeed, canagliflozin was not so different from the empagliflozin and dapagliflozin, and this is a dose-response plot. But it might have a kind of increase in efficacy at the higher doses, but it comes with a price. Canagliflozin is least specific compound relative to SGLT2, and it also inhibits SGLT1. Yes, it's only by, well, only it's a relative again question, 10%, but it's 8 times higher than for empagliflozin, dapagliflozin. May I remind you that these compounds, they should target SGLT2, not SGLT1. And affecting SGLT1 might lead to additional adverse events, which we do not want to happen. So that's a point for concern for canagliflozin. Yeah, that's basically it. So that requires further evaluation. There were trials that highlighted that canagliflozin indeed has a little bit worse safety profile compared to the other two compounds. That was quite an interesting exercise. So we're out of time, and let me switch to the conclusions, just say a few concluding remarks, and if there is an opportunity, we can, of course, switch to the questions. So what this work is about. First, it is about developing a method for the development of QSP models. This method was proposed, and it was also implemented as a software package in R and Molex environment. And I might add that this method was used in the development of CMOOC software. I will talk about it a little bit later. We also developed two mathematical models, kidney glucose reabsorption model and integrated model of type 2 diabetes. We highlighted, we explained the limited efficacy of gliflozins. We compared the efficacy of different gliflozins, and we evaluated the interpatient variability. We quantified it. We proposed which patient characteristics are essential for the efficacy of the compounds. All of this research, it was published in several papers in cited journals, including the Russian Journal of Numerical Analysis and Mathematical Modeling, in CBD-PSP, two articles in Diabetes, Obesity, and Metabolism Journal. Maybe last point that this methodology, it is actively used in our works and the works of our colleagues. As I mentioned before, this methodology, it was used as a basis for domestic software, which was registered in our Ministry of Digital Development this year. I expect that we will soon publish a book. It will be a first book on QSP modeling, because the methodology is relatively new. Of course, it's not new in terms of the mathematics, in terms of the previous attempts at modeling, but again, we are talking about drug development. This is kind of important that we are specified this for drug development. Yeah, hopefully this will be, it will comprise a full chapter of this book, and it's already written. We are waiting for final revisions, and hopefully it will be out this year. That said, I would like to thank you for your attention. First of all, yeah, Vitaly Isakovich, thank you very much for the opportunity to participate in this scientific seminar, and thank you for your time.
Yes, thank you, Victor, for this interesting presentation. And indeed, I'm very much impressed by this systematic approach to such a complex set of problems. You combine very different approaches, literature search, and all this developments, modeling, and many different things. So I suppose that we have many questions to discuss. So please, if there are questions from the audience, we can. It's a good moment to ask them. And waiting for these questions from the audience, maybe I can begin this discussion. And well, there are certainly several very interesting points. Some of them I was able to understand. Maybe some of them I missed. Could you please show this integrated model? I think it's slide 17 or 18, maybe something. Yeah, this one. Yes, this. Yeah, no, this one. Yeah, it's very it's very nice diagram, many things. There maybe not very easy to just catch all of them immediately. Yes, but so all these 44 equations, they're basically here, right, in all these different compartments. But for example, I don't know, you have here this insulin effection, glucose elimination, and other things, plasma insulin. Yes, plasma insulin. Do you have equations or somehow in your model for insulin production, or you put it like a constant production rate or whatever?
No, not exactly. Thank you very much for this question. It's a quite complex equation. So first of all, we should look at here at this equation at this rate. So we have insulin production is driven by glucose, right? We all know, I think we all know, right, that insulin and glucose are like a scales, right? So the more glucose we have, the more insulin will be produced, and the less glucose will, and the glucose will go to the tissues, and vice versa. So we have the following equation. We have a constant I pro. I will show you. It's constant, but it is derived from the steady state value of insulin. But technically, yeah, it's a synthesis constant multiplied by glucose divided by its steady state condition. So in steady state, this equation is equal to 1 in the power of IPRG, which is a parameter. So at steady state, this term is equal to 1. Then we have one more thing. We have incretins. When we take a meal, the gut is stimulated to secrete GLP-1 and GIP enzymes, which are hormones that stimulate insulin production. They potentiate insulin production. So if you just infuse GLP-1, for example, it won't cause an increase in insulin. It only causes an increase in insulin if you have additional glucose, which essentially happens here. So if we have, if you have glucose in the gut, which is glucose in transit compartments, then we have secretion of incretins that potentiate the effect of glucose on insulin production. That's how it works. And then we have clearance. So at steady state, we do not have glucose in the gut, and this term is equal to 1. So we can derive IPRO as clearance multiplied by a steady state insulin concentration.
Insulin resistance, how it is taken into account here?
That's a very good question. So what's insulin resistance? We need to look at the equation for plasma glucose. It's the most complex equation by far in this model, but it's very logical. For glucose, we have 2 types of elimination. One elimination is insulin-independent elimination, and the second elimination is insulin-dependent elimination. And you can see it here in this equation, basically. This is insulin-dependent elimination. We estimate the value of insulin-dependent glucose elimination. It's marked by red. So this parameter is estimated by against the experimental data, and it reflects glucose sensitivity to insulin. we, if I remember correctly, we also did, we expanded this model. It's not listed in the list of publications here because it's type 1 diabetes, but this model was then expanded and already published for type 1 diabetes, where we obviously changed this parameter. We recalibrated it for type 1 diabetes and healthy subjects. And yeah, insulin sensitivity is basically reflected in this parameter. And yeah, it was changed for healthy and type 1 diabetes subjects. It was higher. The clearance was higher, insulin-dependent clearance.
All right, I understand that it's in this insulin glucose elimination term, it's a parameter which is responsible for that, and you calibrate it probably with some available data. Another, well, there are many, of course, the model is quite complex and many things, so it's, I think that it's really, I look forward to consider it in more detail. You understand what I'm talking about.
Yeah.
Well, but there are also many questions, I think, and which might be interesting beyond the model. For example, you mentioned in the beginning or somewhere in the middle of your presentation about drug combination, and I pay attention to that. So, so how this drug acts on the biomolecular level? Do they block some receptors, or what is the mechanism of drug action?
They bind with the site of a transporter. So these drugs are small molecules, right? So these are small molecules that basically, if I remember correctly, they block the well, I should probably say it like entrance of the SGLT2 transporter, because the SGLT2 transporter is just an enzyme, right? It's a sodium glucose co-transporter. It transports sodium and glucose molecules from urine in kidneys and kidney tubules back to plasma. These molecules, the glyphosins, they competitively bind. With the exact, I don't remember the exact sites, but that's that's what they do.
Right, I understand that. But if the drug action on the molecular level is they block receptors, then we can think about the situation where there is a limitation with respect to these available receptors. And in this case, drug combination may not be just their like independent action.
Exactly, and it won't. Yeah, I think I understood your question. In this system, it does not make sense to use combinations of dapagliflozin, for example, with empagliflozin. They're essentially the same thing. They will target the same place,
if this place is available. This is what I'm trying to say.
Yes, exactly. So it's basically
no competition. Yeah. Right.
No. So I would say models like I've been working in diabetes for a prolonged period of time for pharma companies, mostly we solve different projects. For example, speaking of the combinations, it's more, we worked, for example, on slightly different compounds. For example, combination of GLP-1 and GIP agonists, or GLP-1 and glucagon agonists. So when you have two different mechanisms of action, if you have one, yeah, you're essentially competing for the same target. So it does not make sense to test combination treatment. And very, very good example again, but that's another type of work, type 1 diabetes. Type 1 diabetes is always a combination with insulin, exogenous insulin. And this is what we are actually actively developing now. So how to better combine, and well, I have two publications about basically, is there a way to better combine gliflozins with exogenous insulin in type 1 diabetes?
Right. But here in type 2 diabetes, so the drug you are discussing, they try to eliminate glucose from blood plasma, but
Yes.
But it seems to me that this is not sufficient. Something else should be done because our organisms need glucose. Glucose should be absorbed. So it's not just enough to eliminate it.
Yeah, you are absolutely correct. But on the other hand, for type 2 diabetes, there is an excessive amount of glucose in plasma, and technically, type 2 diabetes subjects, they have excessive glucose. With type 1 diabetes subjects, that's exactly the main problem for gliflozins, because the organism needs glucose, and there's a lack of glucose because glucose does not go to tissues because there's no insulin. And major problem with gliflozins in type 1 diabetes is adverse event called diabetes ketoacidosis. Basically, the organism starts to think that we are starving it because glucose starts to excrete with urine, and we decrease the amount of insulin that we administer. Thereby, we decrease the amount of glucose that goes to tissues, and the organism starts to think that we are starving. It produces ketone bodies, which oxidizes probably the word, the blood, which is a very bad condition. And gliflozins were not approved in the US for type 1 diabetes because of this adverse event. They were not approved. Only in Russia and Japan.
There's also another question. Unfortunately, I think that I missed one very important point about this 50% limitation. You explained it in one of the, close to the end of your presentation, but maybe I was distracted or something else and I missed that. Could you please repeat shortly about this limitation, 50%? Yes, this one, yeah.
Yes. This one.
Yes.
Yeah.
So your explanation with you do why is limited by 50%.
So by default, by in vitro experiments, SGLT2 transporter, SGLT2, is responsible for 80 to 90% of glucose reabsorption in healthy condition, right? So right now, I'm not a diabetic patient, so basically 80-90% of my glucose is reabsorbed back to plasma and kidneys through SGLT2 transporter. Then we might expect that when I eat a large dose of SGLT2 inhibitor, I might expect my glucose reabsorption to drop by 80 to 90%, right? Because SGLT2 is responsible for 80-90%. But when clinical trials started of gliflozins, gliflozins were able to inhibit glucose reabsorption by not by 90%, but by 50% maximum. And we explained this phenomena within the structure of our model. The explanation is actually very simple and very straightforward. Because, just a second. Too much equations. Because of the spatial component of the kidneys, SGLT2 transporter, it is located in the first and second segments of the proximal tubules. SGLT1 is located further down the tubules. And we can block SGLT2 transporter very strongly by 100%. But what it does, we basically introduce more substrate to the SGLT1 transporter, which is located further down the tubule. Because, okay, previously most of the glucose went out here, but now we block SGLT2 and glucose moves further to the next compartment, and SGLT1 is not at its maximum capacity. So what happens, SGLT1 starts to compensate, and the reabsorption through SGLT1 increases. That's the red curve. So the yellow curve goes down, it's reabsorption through SGLT2. And red curves goes up. This is reabsorption through SGLT1 because they increase the amount of substrate. And the green curve is percent change in total reabsorption, just a simulated experiment. We see that with a large dose of dapagliflozin, we achieve, well, at max, we achieve around 50% inhibition, as we see in the experimental data, which matches with the experimental data.
Yeah, but if we block both types of the receptors at the same time, then what?
Then we will increase the effectiveness. But the problem with SGLT1 is that unlike SGLT2, SGLT1 is expressed in other organs, including gut and even bones. And the most common and very strong adverse event of SGLT1 inhibition is diarrhea. And these were not developed. The development was stopped.
All right, so we cannot, in fact, block this.
There is one compound called sotagliflozin, which inhibits SGLT1 in addition to SGLT2 a little bit strongly, but again, it has a safety profile. It causes diarrhea and volume depletion. We did the meta-analysis. We have very nice numbers on this, and it's a common fact. So if a patient can bear with this, then yeah, but
yes,
not,
yeah. Yes, sorry. Yes, I understand. Thank you. Well, in fact, unfortunately, we have to finish soon our discussion because it's a little bit long, and I have another meeting in 5 minutes. But I cannot resist to ask. Well, the questions are very big, but if you can give a very short answer about virtual patients. In fact, when we worked on several like PKPD problems, we worked with virtual patients. And I think you briefly mentioned something related to virtual patients. So how do you estimate from the general point of view whether it is really useful to consider virtual patients?
Short answer depends on the question. If you need to statistically prove that most of the population will respond to your treatment, then you need to create some kind of bands. If you want to statistically, bands that will represent the actual variability in the population, and then you will need virtual populations. So for example, when we select the dose, we need, very briefly, sorry. For example, we have a response, a dose response. We need to our subjects to respond, I don't know, above this level, above 80. So we only need to select the doses that provide us with response above 80. I'm just making things up. But how much of the population will respond above 80? This will depend on our prediction distribution. And if we want to consider it, if we want to answer such question, if the population, the majority of population will respond above a certain threshold, we should consider virtual populations.
Okay, thank you very much again. I will leave my last question for the next time. In fact, it was kind of philosophical question about how to use artificial intelligence in all this drug development, but it's a very probably big question, so let us keep it for some other discussion. Thank you again for the interesting presentation and for this interesting discussion. There are no other questions from the audience, so we finish our seminar. Thanks again. Have a good day. Goodbye.
Thank you very much. It was a big pleasure. Have a great day.
Yes, thanks. Bye. Bye.
Thank you very much. Goodbye.